Hi, I'm Robin, a production engineer. Later, I'll be joined by Sumit, a software engineer. We both work for Meta. This is a graph from a research paper on research papers, going over the rate of publishing AI-related research. See that last bit on the right? For 2023, last year, at over 3,000? Yeah, that means that on average, over 100 AI-related papers were published per day. And you know it only went up from there. Now, imagine us poor storage engineers. In our world, things move so slowly that we are still using hard drive technology from literally the 1980s. We've needed to scale things out, sure, but nothing like this. And even how we scale is different. Historically, most of our large-scale needs were for warehouse applications, like MapReduce, where the I/O is constant and streaming with slow ramp up and slow ramp down. There's many independent workers, which means that the throughput, which you can think of as like average latency per size, is what matters for overall performance, so the outliers can be ignored. And we're the big spendy boxes. Storage is the expensive slow part. So it's generally better for an overall project's needs if the storage consumers change their code to make our job easier. Now, GenAI training comes in and hands us a massively different game to play. I/O comes in like a freight train hitting a brick wall. And now it's many dependent workers, which are gang scheduled in a checkpoint ingestion model. So that means that max latency, the outliers, is what matters for overall performance. And storage cost, as we all know, is a drop in the bucket compared to the cost of GPUs these days, let alone the opportunity cost of time to market. So it's better overall for storage to bend the knee, to make the AI job easier. So where do storage and AI meet? This is the 100,000 meter view of the GenAI training processes from the storage perspective. We really only care about the reads and the writes from storage. The 10-second description is that the GPUs read the training data and do their magic in a tight loop, and then every once in a while, pause, save their stuff, and then repeat this cycle until it decides that it's done. Ingestion is all reads. This is where the GPUs read the training data from storage and do their AI magic on it, and then read the next bit of training data and repeat the process. For LlaMa 3, this wasn't the hard part. It turns out that reading text, even a whole lot of it, isn't really all that taxing on our systems. Checkpointing, in contrast, is all writes. Checkpoints are a save state to reload from later in case there's a failure where the training is paused and the GPUs dump all their state, then turn on again. Obviously, we want to minimize that training is paused time, but we also want to minimize the lost work due to failures time, hence saving. Because a GPU training cluster is effectively just one massive supercomputer that happens to use the network as part of its PCI bus, any single machine failure, any GPU, any stick of RAM brings the whole thing down until you reload your save with good hardware. As you can imagine, the more GPUs, the more things that can fail, the more often things fail, the more work you lose per failure, and hence, the more often you should save. This is the hard part for us, especially as we scale up to larger models and more GPUs, because this goes from literally zero traffic to saturating the entire storage fabric, every device, every queue full, within 10 milliseconds. We measured. Also, because every worker needs to dump their entire state, one slow worker means the whole thing is slow. Unlike basically every other use case scenario at scale, max latency, the outliers, is what matters here. And it's under the most degenerate storage situation you could wish for. A huge spike that tries to use more capacity than you can possibly give it. And we need to not only make this work, but work well. So, obviously, we asked them to change the usage to be easier on storage, right? Wrong. There's a new Moore's law in town. AI research rate doubles every 24 months. With over 100 notable changes in the field every day, and remember, that was last year's number, iteration time of new AI experiments is the currency to optimize for. When our AI engineers fetch something new from whatever GitHub attached to whatever research paper, we need that to just work. So here's a helpful, hopefully uncontroversial chart of who we want doing what kind of work. TLDR, AI folks do AI, storage folks do storage. If it takes even an hour to adapt some colleague's GitHub repo to our own storage APIs, that's already an hour too long. Except it doesn't take only an hour, it takes days. And then the continuous tax of maintaining that fork. This is clearly unacceptable. Now these are the storage standards that AI devs are just used to in industry, which we need to just beat. It doesn't even matter if these are good APIs. It's what the industry uses, so it's what we need to provide. We want our AI researchers doing AI research, not storage shenanigans. Except that's not the storage solution that we had. We have something developed in-house called Tectonic FS, designed from the ground up with MapReduce in mind, currently running all major storage at Meta. It easily scales to a much higher max bytes or throughput than anything AI needs. However, although that first point seems nice, and it turns out that append only happens to work for checkpointing, so that's okay, those last two don't really play nice with our needs here. So, we were in kind of a panic. We had a problem and no solution. So we tested a bunch of things. Names redacted to protect the innocent, but we evaluated a whole slew of options, including just buying off-the-shelf products that claim to be specifically for AI workloads. The problem is, Meta is big. Like, really big. And although these off-the-shelf options worked for the size of LlaMa 2, they simply couldn't handle the higher scale of LlaMa 3, let alone what we expected for LlaMa 4. At the end of the day, we came to the conclusion that we needed something that didn't exist. Something that both works and acts like NFS. We need to either improve the scalability of an NFS solution, or we need to make our scalable solution look like NFS. Now, as surprises probably no one attending a conference titled Systems at Scale, it's a lot easier to add an API service to an existing scalable architecture than it is to add a scalable architecture to an existing API surface. We decided to wrap Tectonic in a fuse wrapper to mount it like NFS. Now, remember this slide? Every so often, all the GPUs dump their state to storage all at once. Remember this diagram? Did you notice that crazy range that spans 8 orders of magnitude? That's 4,000x between the high and the low. That's not just, we can't show you the real numbers. The range really is that crazy. We would regularly wake up to a message that, oh, by the way, we 60x'd the checkpoint size last night. This caused something of a stir throughout the storage org. See, the way we've always done things is to get the requirements from the client, who would be AI in this case. We would build a system to those max requirements, and then if they go over, well, that's on them, because how can you possibly build a system to handle anything? But we had to flip that on its head. With the rate of change in the AI industry as a whole, not only could we not know the size, but the AI folks couldn't either. We simply had to handle the possibility of hitting the ceiling. And that mental shift was difficult. So we set this up at breakneck speed and breaking a lot of eggs as we went, leaving trails of tears, getting to the point where we could test this end to end. Testing on real GPU hardware at scale was entirely too expensive, of course, so we developed a way to test the storage for the AI workload by literally running the full training workload, but with garbage random data instead of actual GPU computed data. We ran this against all of our test clusters and everything seemed fine. But then the checkpoint size grew by a factor of 70 this time. Overnight. With no warning. And it turns out that while Tectonic could handle as much scale as you gave it machines for, if you ever somehow touched the ceiling, everything fell apart. Goodput dropped to about 5% and stayed there for hours, which is, embarrassing. But in our defense, well, nothing could ever really do that before. Storage needs change slowly. And in general, we actually want to service the load that we receive. So we've always just stayed ahead of the curve, grown the cluster to be big enough for our needs. We'd never hit the ceiling before. Now I'll hand you over to Sumit to tell you how we engineered our way out of this mess.
Thank you, Robin. Hi, I'm Sumit Gupta. I've been at Meta for about 4 years. During this time, I've been focusing on flash storage and recently flash storage for AI. As Robin mentioned, when AI traffic came on board, it came on board with its own set of unique requirements. So let's see what are some of the things we did to address those requirements. So when AI traffic came on board, we were already running multi-tenant traffic on large shared clusters. And with AI came AI checkpointing. Now what happens in AI checkpointing is all the GPUs, they pause and they dump their in-memory state to persistent storage in a very synchronized manner. You can see on the graph on the right-hand side that generates huge spikes. And these spikes then started interfering with other tenants. And as you can see, other tenants, they started violating their latency SLA. Now, normally we would have rate limiters in place to handle these kind of problems. But here, the rate limiters could not respond fast enough. So what was really going on? What was going on was that AI traffic was building up in milliseconds and rate limiters needed second level granularity. So this exposed some gaps in our tenant isolation. And while we started working on those gaps in parallel, we had to move forward and we decided to build dedicated AI clusters. With that out of the way, the next thing we had to now handle is IO supply. We had to figure out how much IO supply is needed for AI. Now, our existing clusters were designed to support most generic IO shapes. We have tenants which were running small block IOs looking for lower latency, as well as tenants which were running large block IOs looking for more throughput. So, because of that, we were not tuning for best bandwidth per terabyte per se. But looking at AI traffic, it felt that because we didn't really know much about how much bandwidth or latency AI traffic needs, but talking to some of the researchers and looking at some sample workloads, it seemed that AI traffic needed more bandwidth and not so much on the latency side. So looking at the bandwidth per terabyte needs, they were actually much higher than what we were providing, sometimes 2 to 3 times higher. But this was easy to handle for us because we had already made the decision to build dedicated clusters for AI. So we recharacterized those workloads and made sure that we only support the AI specific shapes. This allowed us to increase our overall supply by 4x. So we were now able to serve the AI needs. So once we started running some sample initial workloads, we saw some interesting phenomena happen with goodput. Even though the throughput of the cluster was high, but the goodput was starting to drop. So what was going on? Looking at the traffic in deep, we found that as the checkpointing started, it started pushing more and more IOs. Sometimes thousands of IOs, they started building up on the clusters and especially hotspotting the cluster. And as these queues got deep, the number of failed requests also increased. But the throughput overall at the lower layers of the cluster was pretty good, whereas the goodput at the upper layer was not very good. It seemed like we were wasting a lot of IOs. So we started debugging deeper into, okay, what is going on? So then we started looking at IO scheduling, and we saw that IOs were timing out. And the reason they were timing out is that queues were getting deeper in the lower layer. And the clusters are designed to deliver lower latency. So when they see some IO does not return for like a second, they start retrying, they start failing those IOs. And that actually generates even more IO, and the queues got even more deep. So overall, the lower layers were working very hard and delivering high QPS and high throughput, whereas the upper layers were not seeing that much throughput, that much goodput, and more failures. So we determined that we need to reject the IO sooner. Now to implement that, we looked at these two concepts, control delay and adaptive LIFO. So what is control delay? The idea here is that if a queue is not empty for last n milliseconds, let's say about 1000 milliseconds or a second, then the amount of time we want IO to spend in that queue is about m millisecond, where m is much smaller than n, which is about 100 milliseconds in this case. So this will allow us to flush the queue much faster if the IOs are getting stale. Adaptive LIFO is an idea that if the queue is building stale IOs, then rather than serving it in a first in, first out manner, we start serving it in a last in, first out manner. So we are picking IOs which are more fresh first and letting the IOs which are stale time out and then get retried somewhere else. So then we implemented these concepts and we saw the queues were much more empty and our overall throughput increased and overall goodput also increased. We used the value of 1 second as queue timeout and 100 millisecond for queue timeout when the IOs got stale. And then we will wait for the queue timeout to get lower, and as long as it is stay within 100 millisecond, we would bump it up back to 1 second. So what are the outcomes of this? Not only that our goodput improved, our P99 latency for successful IOs also improved. Obviously, it was much higher throughput, because we were not spending time on retryings or failing the IOs. This also helped us avoid hotspots, which means that IOs were actually now getting retried somewhere else and providing much better cluster balance. And lastly, this made the cluster more scalable, because now if we needed more IO, we could just add more nodes. So we could predict that for a given AI need, how many nodes we need. Now, as we were going through this exercise, we found some other things which we could improve in the clusters. These were side effects or side things that came out as a part of this exercise. One of the things we found is that the memory bandwidth on these nodes were getting saturated. And that's because the network is spiking. As network traffic increases, the consumption of memory bandwidth also goes up. So to limit that, we can limit the network traffic. The second thing we found we could limit is kernel handoff time, which basically means you give an IO back to the kernel so that it can be transmitted back to the client. But if the network is congested, all of that data is sitting inside the kernel and it's causing out-of-memory errors on the net node. So to avoid these out-of-memory errors, we started limiting the kernel handoff time. And once we were starting to limit these two parameters, we found that there are other deadlines which we can also tighten up, and that will also improve our resource reservation and overall behavior of the node. Another thing we did is we started building tools to recreate AI-like traffic so that we could run simulations and see some of the tunings, how they are behaving and how they are producing results. And lastly, we noticed that all of this is happening because we do not have good flow control and rate limiting. So we started putting some investments in the area of implementing flow control and limiting IOs at the front itself. Now with that, back to Robin.
Thank you, Sumit. So now we know we can handle massive spikes, even that go from 0 to overwhelming the entire cluster inside of single-digit milliseconds. We're ready for whatever AI can throw at us. And as a bonus, it turns out, if you can have a super scalable distributed file system mounted on your local machine that looks and feels like NFS, well, that lowers the barrier to entry for a lot of non-AI projects as well. We have a bunch of internal projects knocking at our door right now. Probably the most lasting change, though, is in how we think about storage systems at scale. I said the thing. Instead of being all but forced to hide behind our walls of tradition for business reasons, reacting to slow changes in industry with multi-year iterative improvements, we are now out front, blazing the path in front of GenAI, so that if they do have to slow down, it certainly won't be because storage isn't keeping up.